Hello everyone and welcome to this video. You finished your ANSYS simulation and your bolt carries X amount of shear force, but is the bolt actually safe? ANSYS won't answer that question alone. So in this video I will show you exactly how to verify the bolt against shearing according to VDI 2230 using a real finite element model. And at the end of this video, I will give you a free Excel calculator that performs this check automatically for you. That check will be done using this table, so I'm gonna to explain that for you in a moment. So let's get started. In this example, I already prepared a bolt plate connection in ANSYS. The contacts, preload, and boundary conditions are already defined, so today we will focus entirely on the engineering evaluation of the bolt. This objective is simple. Extract the shear force from the simulation and determine whether the bolt is safe according to VDI. So before we go to the table, all what I did in this simulations model, we have two plates. We have already defined a support on this face and a load on the top face, and I have a frictional contact with a frictional coefficient of 0.12 used. We have 4 bolt M8 used with a strength class of 8.8. The bolt pretension used in this simulation was 18.6 kilonewton. In case you are interested to know where this value comes from, you can check my previous video about bolt pretension, so you can see according to VDI how you got the bolt pretension for each bolt size and strength class. Now let's go to the table. So before we look at the ANSYS results, let's first understand this table, because these values comes from the material properties and VDI 2230. The first row show the bolt strength class. As you can see, we have the 8.8, 10.9, and 12.9. The second row is the minimum yield strength for each one of these bolts, which is a little bit different for the 8.8, because for smaller bolts for M16 or lower, they have around 640 megapascal as yield strength. The bit bigger bolt, they have bit more yield strength, which is according between 640 to 660. And for the 10.9, we have 940, and for 12.9 we have 1100 megapascal. The next row is the ultimate tensile strength. So this value is very important because VDI 2230 calculates the allowable shear load using the ultimate tensile strength and not the yield strength. So many engineers make the mistake of using the yield strength here, which is lead to incorrect results. The next row is shear strength reduction factor. Because bolts are weaker in shear than a pure tension, so VDI 2230 reduces the allowable stress using these factors. For example, grade 8.8 uses 0.65, while grade 12.9 uses 0.6. Now, the next row we have the shear force, and here we enter the shear force acting on the bolt. These values will come directly from our ANSYS simulations. The next row, we need the effective cross-sectional area resisting shear. So in this example, the shear plane passes through the threaded portion of the bolt, so we use the tensile stress area of around 36.6 in our case for the M8 bolt. So let's dip there on these 4 cells, the 36.6. You don't need to enter on all of these cells, but I'm gonna to do it right now just to see at the end the difference between if we change or increase the bolt strength, what will happen to the factor of safety against shearing. So we tipped like this, 36.6 millimeters square, and finally we will get the actually the table calculates the safety factor against shearing. So a value greater than 1 actually in most cases means the bolt satisfies the VDE requirements. It's be recommended to be more than 1.1. So, of course, in practical engineering, we usually require a much larger design margin depending on the application. So it could be like more than 1.1. It depends on the application and how important it is. So now let's go back to the model. And now let's determine the actual shear force acting on our bolt. So this is the bolted plate connection used for this example. And the bolt is already preloaded, the contact definition are already completed, and an external load is applied on the upper plate. So after solving the model, we can extract the reaction force acting on the bolt, and we can do that by just going to solution, right-click, insert, and I will go to beam results because I already modeled the bolts as a beam. So I can benefit from that and use beam result and choose shear force in my case here. And let's evaluate the result and see. So as you can see, the maximum like overloaded bolt on our case or loaded bolt on our case carries approximately like 2086 Newton of shear force. Now the interesting question is, these bolts actually safe? So let's verify manually before trusting like any spreadsheet. So we write like slowly for 8.8, we will go to the table and let's go it slightly to the right, move it. So for 8.8 bolt, which is in our case actually, we have a yield strength of 640, but it will not use in this calculator because, as we told you before, the safety factor is like according or use the ultimate tensile strength with the shear reduction factor to determine the safety factor. So the ultimate tensile strength here, it's like 800 megapascal. We have a reduction factor of 0.65, and multiplying these two parameters together, dividing by the shear cross-sectional area that we have, we got the maximum allowed shear strength and our shear force, what we got from this analysis, which is 2086 Newton. So let's write it, 2086 Newton. We got like finally a safety factor of about 9.1. So that means the bolt has a safety factor of approximately 9 against shearing. So clearly this bolt is very safe under the applied load we have in this model. Now let's compare the different like bolt grades. So if we increase the bolt grade from 8.8 to 10.9 or to 12.9 for example. So all what I have to do is to insert or input the 2086 Newton. And notice how the safety factor increases, the bolt strength like increases, but actually we have like a small like increasing in safety factor, to be honest, in this model. So this comparison like help us to decide whether like increasing the bolt grade is actually necessary, like, or simply increases cost without significant benefit. According to the results, actually we can like still use the 8.8 strength class M8 bolts and no need to use like higher strength class. So one important point before we finish, so passing the shear check does not automatically mean the bolt joint is safe. Depending on your application, you should also verify like the bolt preload, tightening torque, plate failure, bolt tension, and combined loading and fatigue. So shear is only one part of a complete bolt design according to VDE 2230. So to save your time, I created this Excel calculator for you to be used. So simply enter the bolt grade is already like entered in this table. all what you have to do is what's marked in blue actually, to insert the shear force that you got like in your ANSYS model or in any other like FA software, and to give the cross-sectional area for the used bolt in your model. And you will get then automatically the safety factor against shearing. So I'm giving it like away completely free, so just write me in the comment section below and I will send it to you. Also let me know like that you would like more like VDI 2230 tutorials like this one, so I will be glad like to create videos about them. So in today's video we check the safety factor against shearing for a bolt. But how do we calculate the stress inside a bolt when we apply a tightening torque, which is not visible to us in ANSYS models? For that, in the next video, I will show you exactly how much tightening torque creates stresses in the bolt and how to verify that the bolt does not exceed its allowable limits according to VDI. So if you don't want to miss that video, consider subscribing and I will see you in the next video.